Our next speaker is Daniel from Federal University of Rio de Janeiro. He's going to talk about time reversal of waves in random media.
Okay, thank you. Good afternoon. First of all, I love to thank the organizer for the invitation, and I will talk about some things that I was doing back when I was a PhD student, and after that when I was a postdoc. But it's always interesting to revisit these things because it is quite interesting and surprising. And Andre told me that a lot of people that will be here in this workshop are people from applied mathematics and probability, and this is exactly one of the this topic is very interesting because it mixed exactly these two topics in a very interesting way. So, but this is what I plan to talk about. And well, this is a cartoon that appeared in the Scientific American in the last century. So this is very interesting. And the first time I saw this cartoon, it was Professor Jean-Pierre Fouque. He was presenting a seminar here at IMPA, and he talked about time reversal. He presented this picture, this cartoon, and it was very interesting. He's a very passionate French, and he talked like, and I became very interested in this kind of phenomena. And well, Andre told me that it was very good if I tried to do simulations and learn some theory to apply in this topic. And after that, I got my PhD on this topic. So, what is exactly this picture? There is a guy who will talk to the wall, and he will try to will say hello to this wall. But this is kind of a very special wall, and the acoustic waves that come to this wall, they will not just reflect. They will happen something more. What is going on in this wall is that the first impulses that came in will be sent back last. So when after that, after some time, what it will come into the mouth of this guy is like ole and not hello. So this is because this will act as a time reversal mirror, which means that the signals that are coming will be recorded and they will be sent back, but with the duration of time reversed. And actually, there is a device that do that, and this is a very interesting. There are a lot of studies, experimental and also theoretical. From the experimental point of view, there is a group in France, led by Professor Matthias Fink, and this is actually from a paper of him in the Scientific American. What we have is the following: you put a source in a medium, and this source will send a wave, and these signals will travel through this medium, and you will put some microphones, let's say, or a way to record the signals that came in, and then you will play back these signals from this device, which is the time reversal mirror. And what will happen is that, because the wave equation has this time reversibility and this symmetry, the signal will be propagated back to the source. But this can be done perfectly if we have all the information. But in practice, the information that we can get is partial. So the wave will refocus, will goes near to the place where the source was. And this is a phenomenon that has been studied for several years after these experiments were presented. And the main result is that there is a very interesting phenomenon when the medium is heterogeneous, that is super-resolution. This means that actually the heterogeneities enhance the quality of this refocused pulse, or this refocused signal. This is attributed to the fact that there is multipathing in this medium when there is heterogeneities. And another very interesting property is that we have a property that is a statistical stabilization, which means that if you look at this medium as a random medium, that doesn't matter what is the random part of this medium, because the main part of this refocused signal, of this refocused wave, will be independent of the realization of this random medium. So there are potential applications for this phenomenon, and for example, in communication, medicine, geophysics, and underwater acoustics. There is a recent book by Full, Garnier, Papanicolaou, and Solna talking exactly about this topic in the context of randomly layered media. This is a book from 2007. Unfortunately, it was not impressed when I was a PhD student. And that is a lot of information and a lot of results, very, very interesting, a lot of theory, and even if they are applied basically to this problem, there are a lot of methods of applied math that can be used in other problems, for sure. So, but talking about the possible application, there is the possibility to do underwater communication using time reversal, and also to treat destroyed kidneys, stone kidneys. So you want to record, you have a source, and there is the kidney with the stones, and you will record the reflections, and then you will amplify these reflections and send back in this medium, and this is a heterogeneous medium, so they will focus in where the stones are, they will destroy these things. Okay, so during my PhD, I was very interested in this type of phenomena, and there was one thing that was very important for us, which was the robustness of this kind of phenomena, as they can be observed in experiments. So that means that some perturbations will not actually change the phenomena itself. So we think about this situation in which there is a random medium. So I will send an initial pulse. I will record the reflected signal and send back to the medium, and I expect to see here something that resembles the initial pulse. But what if between the direct propagation and the backward propagation, we change the medium, and this is the main goal, and this was the main goal of my thesis, to describe what is the signal that will appear here. Okay, I will show the case in which we work in a one-dimensional layer medium, and here are the equations for the one-dimensional acoustics, linear acoustics, and these are the rho and K are the describe the properties of this medium, the density and bulk modulus. We are going also to use to work in this asymptotic regime where there is the correlation length of the fluctuations of the medium divided by the width of the poles are approximately equal to the width of the poles divided by the propagation distance. This allows us to propagate a pulse for a long distance, and he will travel, and it was there would be since the medium is heterogeneous, this will the poles will travel and feel this the fluctuations of the medium for a long time. So because this is smaller than 1, and this is the regime which is more interesting because it is a regime where we can see some diffusive phenomena that appears when waves are propagated in random media. So actually, what we do is that the density and the inverse of the bulk modulus are modeled using background density and random fluctuations. So we used to put some, we need to put some restriction, just technical restriction on the behavior of these random variables here. So using that, we can obtain characterize the propagation sound velocity in the medium, the acoustic impedance, and the travel time. And as I said, I will use an initial pulse that his width is larger than the correlation length of the medium. As we see here, the correlation, the fluctuations in the media are scaled with epsilon square, and here we scale the impulse as epsilon here. So what will happen is that, okay, so as I said, I will send the first pulse in this random medium with fluctuation. This is the forward medium, and there is a backward medium where the backward propagation will happen. So let me show. So this is a very simple simulation. This is the derivative of a Gaussian, and here is the medium. This is a random medium. Actually, I will run two simulations of this forward propagation. And as the pulse propagates in this part, which is the random part, there is a reflection, a reflected wave that will be recorded and then sent back into this media. In this case, I will send back this recorded signal exactly in the same media. So this is the signal that was reflected for these two media, and then they will propagate, imping the media, and after some time there appears this signal, which is clearly is higher than all the fluctuations in this wave, and this is very related with the initial pulse that was the derivative of a Gaussian. So in the general case, what we can do? So we'll consider that there is two media, the forward and the first media where there is the forward propagation, and a second media where there is the backward propagation. So after some works, we can describe the reflected signal, and this is a combination of Fourier transform and the use of the reflection coefficients. One of them corresponds to the forward medium, and the other to the backward medium. And there is this function J that is related to the property of the time reversal mirror. And in this case, it's just it makes a cutoff of the reflected signal and use this interval. This is quite messy, but we can do some asymptotic analysis, and this is what we get. In the limit when epsilon goes to 0, what happens is the following, that if we observe the time reverse reflected signal at time T1 different from T0. T0 was the time associated with the recording time. So we will see nothing. But as this is a limit, this is why sometimes we see that there was just some fluctuations in the reflected wave. But at the appropriate time, that is when T1 is equal to the recording time T0, we will have this signal. And this signal can be completely characterized. And this limit is a limit in distributions. And we can completely characterize this signal through this convolution. And there is a Fourier transform here. And this function here satisfies a very kind of, it's not very complicated, but it's a Bauer Ito stochastic partial differential equation. So in principle, when we have two different media, we will have that this kernel here, which is the refocusing kernel, will be a random function. So this is the W will satisfy this equation. We have to take this limit. So we need to solve this. So in principle, we need to solve this, and this will be, in principle, a random function. But there is some cases where we can actually obtain a function which is deterministic. For instance, if this is 0, that means when the velocity in the forward and the backward medium are equal, then this part, which is the random part of this equation, will disappear, and this is just a parabolic PD, a deterministic parabolic PD. So this is a very interesting case that we want to use, because we want to see this stability of this phenomenon, but not just when the two media are equal. So we can actually observe that if we take these numbers, this is the supremum of this set of points, and the infimum of this set of points. When this is equal, we can see that this is actually, this will be always greater than this. But in the case when they are equal, then we can show that this function will be a deterministic function. So the kernel will be a deterministic function, and even if we have two different media, we will observe we will have a statistical stability in this case. So this is the case when we have these two media. This in blue will be a constant velocity, and red, the velocity will have this, will decrease and then increase. And in this case, we will have that Z0 is equal to Z1. And this is the result of several experiments with this. And this is in the case when the two media are equal. And this is exactly the case when the second media is different. But we see that there is actually a very clear refocusing here that independence of the basically of the realization of the media. So what else? I spent a lot of time talking about this first part, and I will want to present a way to use this phenomena to in a detection problem. So as we see, we are interested in making some time reversal experiments in order to detect some changes in the medium. So we want to use time reversal to determine is the velocity in the sound velocity in the first medium, where we do the first part of the time reversal experiment, is equal to the velocity in the second medium or not. So to this, we also will consider that there is some, the measurements are not exact. So there is a noise in this reflected wave because of the measurement device. So we can also make a little bit different way to make this time reversal procedure in this case, because we will work with the difference of two reflected waves. So we will produce a first experiment here and record the reflected wave. Then after some time, we will make another experiment and we'll record the reflected wave, and then we will use the difference of these two waves, of these two signals, and send back on the last medium. So if these are the same medium, this will be, we will just send basically a null signal, and there will be nothing to see. But if these two media are different, we will see two different, we will have a signal which is different from 0, and when it will be sent, we will have something that is also a coherent signal. So it happens that we can characterize in the asymptotically this time reversed difference reflection, even when we consider that there is a noise in the in these measurements. So and it is actually, this is the case that it will be actually a Gaussian, will be a signal which is how to say, it's a deterministic signal plus a Gaussian random noise. So we will push reformulate this detection problem as a hypothesis testing problem. So this will be the hypothesis that we want to test. The two velocities are equal versus the two velocities are different. And this, because of that asymptotic behavior, will be, can be put in the form that we want to check if the sample from a Gaussian, a normally distributed variable, is the mean is 0 or not. And we have this test, which is a modified maximum likelihood ratio test. And we apply this test, and these are the results, numerical results that we have. This is the same medium as before. And what we have here is that we fix the significant levels of this test, and we want to know what is the probability of detection. And theoretically, in these cases, these are the probability of detections, and what we see with these points in red are the results that we obtain after a lot of simulations, and this is very, there is a good agreement between these results and the theoretical results. Other things that we do is that we can study the influence of the sample array and the number of points in this sample. And what we observe in this case is that we can, in some, use here, for example, the sample array is 0.01 for this case, but as the number of points is 100, the result is very similar. So this is a bad result. So because the probability of detection is very low in this case. So, and when we double the number of points, so we see that the curve goes more near the one here. It would be a good probability for detection, and we can actually understand this behavior by doing some asymptotics with respect to the parameter m. So, well, we analyzed, yes, the influence of a changing medium in the time reversal of wave, and we used this analysis to understand, to obtain some situations in which we can observe the statistical stability. We made some simulations, and we also use this to present a way, a method for the detection of changes in a random medium. So thank you for your attention.